Today, we're going to look at a small, almost invisible idea that helps your code run so much faster. It's a really simple solution to a surprisingly tricky problem that's happening inside every single compiler. So let's just start with a basic question. When you hit that compile button, how does the machine even begin to make sense of the text you just wrote? You might think it just reads one character, then the next, and the next. But it's not quite that simple. A single character, like a greater than sign, doesn't really have enough context on its own. The computer actually needs to see what comes next to figure out what it means. Okay, so let's get into it. The part of the compiler that does this initial reading, it's called the lexical analyzer. You can kind of think of it as the eyes of the compiler. Its whole job is to scan the raw text and group characters into chunks that actually mean something, like keywords or numbers or operators. And this brings us right to the main challenge for a lexical analyzer. It's a problem that we call look ahead. The analyzer is constantly trying to figure out where one word or symbol stops and the next one starts. And to do that, well, it has to peek at the characters that are coming up next. This is a perfect example of the problem. When the analyzer sees this greater than symbol, it can't immediately know what it means. Is it just greater than? Or if the very next character is an equal sign, the meaning completely changes to greater than or equal to. So here's the key takeaway. The lexical analyzer can't just live in the moment. To understand the character it's looking at right now, it has to see a little bit into the future. This need to look ahead is absolutely fundamental. So how do compilers actually solve this? Well, to handle this need for look ahead in a smart way, designers came up with a really simple but powerful technique, the two-buffer solution. First off, what even is a buffer? It's really just a temporary holding area in memory. Instead of reading your code one character at a time from a file, which is super slow, the system just grabs a big chunk of it, like, say, 4,000 characters, all at once and dumps it into this buffer. It's kind of like grabbing a whole box of Legos instead of just one tiny brick at a time. Now, to manage this buffer, the system uses two little pointers. One is called lexeme-beginning, and it just marks the start of whatever word we're currently looking at. The other one, the forward pointer, scans ahead one character at a time to find where that word ends. And the process is really seamless. The forward pointer just keeps on moving. When it hits the end of that first buffer, the system automatically loads the next chunk of your code into the second buffer. Then the pointer just hops over and keeps scanning without missing a beat. And when it gets to the end of the second buffer, it just reloads the first one. They just work in a cycle, back and forth. This is a pretty great system, right? But it does bring up a tricky little question. What happens if a word, or say, a variable name, gets cut right in half, right at the boundary between the two buffers? And that is exactly why we have two buffers. While that forward pointer is scanning ahead in the second buffer, the first half of our split word is just sitting there safely in the first buffer. It won't get overwritten by the next chunk of code until the analyzer has seen the whole word. It's just a simple, really elegant safeguard. But we can make this whole thing even more efficient. Let's look at this one other really clever optimization the compiler designers added on top of this system. It's a little trick called sentinels. Think about what that forward pointer is doing. For every single step it takes, it has to ask two questions. First, what character is this? To see if it's the end of a word. And second, am I at the end of the buffer? So it knows when to load the next one. These checks are happening millions and millions of times. So, can we do better? The solution is just wonderfully simple. We just place a special character, a sentinel, at the very end of each buffer. Now, this sentinel character has to be unique. It's something that could never, ever legally show up in your code, like an end-of-file marker, often just called EOF. Its only job is to be a stop sign. And here's the magic. Now, the analyzer only needs to ask one question. What character is this? It just scans along, checking characters to see if they end a word. And if it happens to hit that sentinel, well, that same check also tells it that it's at the end of the buffer. We've combined two really frequent checks into just one. It's so much more efficient. Okay, I know this all seems pretty technical, but why does a small optimization like this actually matter in the real world? It all comes down to scale. Reading input is one of the most basic things a compiler does. So by making this process faster, we cut down on the overhead and we make the whole compiler more efficient. It's a tiny optimization, yeah, but it's applied to a problem that happens constantly for every single character in every single program you ever compile. In fact, compiler technology is so important for performance that the famous Dragon book on compilers points out that it's often used as the benchmark for designing new computer hardware. And these small, foundational ideas, like input buffering, are a huge part of what makes all that performance possible. And I think this all leads to a really nice takeaway. When we think about great engineering, we often picture these massive, complicated systems. But sometimes, true elegance is in the quiet, clever ideas that work perfectly, millions of times a day, completely hidden from view. Input buffering is one of those ideas. Just a simple, thoughtful solution that makes everything else work a little bit better.